Okay.
All right, Roger. Thanks for actually being generous to lead 2 weeks in a row. I'm going to turn things over to you to keep us going on chapter 3 on statistics.
Okay, so let's see. I don't think I need to optimize those, but tell me if you can see that.
Yeah, we see screen.
Up. Okay. All right. The first warning caveat here is it's very windy up here, and we've had at least one power outage and a couple power stutters in the last 20 minutes. So hopefully we will get through. But if I disappear, that's probably why. Also, Ted, I have a small screen today, so if you can keep an eye out on the chat and interrupt if needed. It's hard for me to have that open at the same time. So I think that we left off here at 3.3, and this was kind of the introduction of the frequentist statistics. And I think this might be one of the areas that is important. And we might spend a little bit of time is trying to understand the difference between the two. But this simple statement, and I think it's kind of repeated a little later, was one that helped me a lot, where the statement is Bayesian statistics treats parameters of the models just like any other unknown random variable, and applies the rules of probability theory to infer them from the data. I think it contrasts later on where how that differs from frequentists. This other part seemed like an important one, which was what drives people to frequentists is this desire to avoid these priors that I've read quite a few different places where we talk about. It doesn't seem like a good thing that your conclusion varies from scientist to scientist based on the prior that they impose upon it. So that's another important one. Okay, so I'll just read it. Please interrupt me. I'll try to skip ahead as quick as possible. The basic idea is to represent uncertainty by calculating how a quantity estimated from the data would change if the data were changed. It is this notion of variation across repeated trials that forms the basis for modeling uncertainty used by the frequentist approach. By contrast, the Bayesian approach views probability in terms of information rather than repeated trials. This allows the Bayesian to compute probability of one-off events. I don't know that the one-off is the critical part of it, but you get a better understanding of way to capture kind of the uncertainty about the parameters, what the unknowns associated with the parameters. And anybody want to offer a comment or flavor on that?
Yeah, I'll hop in and just say that I generally did not like this section at all. I get where he's coming from, but there's like some like huge holes in his explanations that are kind of weird. So I'll just be providing color commentary all night, I guess.
Okay. When you say this section, you mean
the part on frequentist statistics specifically. The other stuff that's kind of in his lane is all generally, I think.
Okay. All right. So just interrupt then at a point where you want to add color. So here we go, 331. In the frequentist statistics, uncertainty is not represented by a posterior distribution of a random variable, but instead by sampling the distribution of an estimator. And we talk about in the context of parameter estimation, that estimator would be returning the parameter vector. So I think what this is indicating is that isn't that a delta? Is that little delta, that little squiggle? So I think that's the estimator here in a parameter estimation context. So the estimator returns from the data D the estimated parameters. Okay.
Yeah, so like if you have some data that you've collected, then it has one mean. That's all it has. But from a frequentist view, you're looking about, well, what if hypothetically you did this a bunch of times? You might get different values.
Right. And it seems like this, was there another one?
Oh yeah, and just to add on to that, the estimators are not, in frequentist procedures, are not typically like the same as a model parameter. So for example, if you had data from a Poisson distribution as a frequentist, you would be comparing the means directly between two groups. You wouldn't be estimating a lambda necessarily.
Okay.
Right. You're interested in the expected value and the X bar, not necessarily the lambda, which is the log of that.
So that would be if you were just comparing two distributions of the same family, as you're saying, is that right?
Right.
Okay. So, but here in the context of we're trying to figure out the parameter theta, then you agree with that last sentence, then, is that right? That it's, well, I guess it's a definition.
Yeah.
Yeah. Okay. Okay. So if I'm reading,
just to clarify, so the delta here is, I think he also uses delta for the Dirac delta function, right? But here it is an estimator, right?
Yeah, I think that's true, at least mostly.
Okay.
Yeah.
I think here it's still the delta function, though.
It is.
I think he's just saying that all of the probability, so to speak, is on this one value, because for your given data set, that's the only mean or the only whatever that you have.
I took delta as short for decision function.
Sorry, Neil, you're going to have to help me out. How is that different?
Yeah, so in his definition, he explicitly calls out like decision theory and a decision function. So you know, delta is for D for decision.
Okay, cool.
Okay. So,
right.
So what we're talking about here, I think, is that they're coming up with sample distribution results that we'd see if we applied the estimator multiple times to different data sets sampled from the same distribution. And each one comes up with a parameter estimation. You get a distribution then of those estimated parameters. And it's the characteristics of that distribution, I think, is what they're is capturing the uncertainty in the parameter. Does that sound right?
Mm-hmm.
Okay. So let's see. Yeah, now apply the estimator to each DS to get an estimate of the parameters. This was my little question mark here is I wasn't clear if that delta and that delta were the same. Because it kind of looks like this is the decision delta and this is the Dirac delta.
Yeah, I think you're right.
Okay. All right.
Just to make it very clear.
Yes. Okay. Let's see. So so they're looking for the distribution induced by it. So now that's my complete understanding of kind of the difference between the two. Bootstrapping. So if you have a distribution defined by a data set, it sounds like there's two different ways that they come up with these data sets to sample, or sample data sets, sampled data sets, I guess. These are multiple data sets, each of which is sampled from the same distribution. In the first approach, there's the parametric bootstrap, which I think what they're saying here is that they're coming up with, this is S, so this is all of them. They estimate the parameters once on the entire data set, and then they're generating sample data sets using those parameters.
Right.
And yeah, go ahead.
So the other thing to look at here is it's like calculating like an error or a residual for each data point in your set, and then resampling those versus resampling the raw data. That's the difference between these two procedures.
Okay. That kind of makes sense.
And ultimately, if I got this right, in the first, the parametric bootstrap, basically, you need to be able to generate the distribution. So if you were saying Like what likely are we going to get if I flip a fair coin 100 times? Well, actually, I have access to a fair coin, so I can actually do that. I can just flip it 100 times, and then that's trial number one. I can flip it 100 times. That's trial number two, and I can do as many times as I want because I have access to the ability to generate those, right? Whereas for other stuff, you don't. You just have the data you collected out in the wild, and you have one set of data. So then as an alternative, you can do the second thing, the non-parametric bootstrap, where you sample from your data with replacement.
Can I pose a question, Ted, there? My assumption was that the D represented a number of coin flips, and all your decisions were based on that one sequence of coin flips. That sounds a little different than the idea of flipping it 100 times, and then that's one sample data set, flipping another 100 times, that's another sampled data set.
Well, I think with his notation, like you see that D superscript S whatever. So that's where I'm saying S is like 100. You're doing 100 coin flips or whatever. But then to the right of that, he's got N equals 1 to big capital N. And that would be how many trials you did of 100 coin flips.
Hey, Ted, I think there's 100 in this case is N, and the number of
other way
data sets,
around.
like how many, yeah.
Shoot,
Because he's saying
okay.
each of size N on line 27.
All right, I got the two of them backwards, but anyway, sorry, but the gist is, right, that you have some experiment, you've collected data, so it could be 100, it could be whatever data points, and you're imagining what if we did more experiments that collected the same number of data points, but they from the same distribution, but they just might be different. So if I'm observing deer in the wild, I don't really have the ability to generate more. So I have to, if I'm going to do anything, I can do the non-parametric bootstrap, which I didn't even know was the non-parametric bootstrap. I just heard of it referred to as the bootstrap up until now.
Okay.
What is the distinction between theta star and, I didn't quite catch that, theta star and theta hat?
My assumption was that the theta star, I think, in fact, they reference it right here.
They say it's the real one, the true parameter.
Right. Whereas theta hat is the one that is computed from the data set using the, what did you call that? The estimator,
Right.
Yeah, so like you flipped a coin 100 times and you got 40 heads, so theta hat is 0.4.
Yeah, but
theta star is what is your unknown that you're trying to figure out. Is it really 0.5 or is it not a fair coin? Is it some other value?
Right, but he, here when he says xn sampled from on line 31, xn sampled from p of xn given theta hat. Why is that theta hat and why not theta star?
It's a plug-in estimate from plugging in the point estimate that you got from an actual data set.
Okay. But we are not changing anything, because all we have access to is the coin, right? Whether it is theta star or theta hat is sort of, in a way seems immaterial because that's all you have is the coin to toss. Does that make sense? But maybe I'm splitting hairs, but yeah.
Yeah, so
way,
for your particular data set, maybe you got an unlucky thing and you got, I don't know, 8 heads out of 10 or whatever, right? And so if that happened and you have a lucky data set, then that's gonna shift your plug-in estimate of the sampling distribution versus the truth, right?
I see. Yeah. So it's
Could be
based on
bad,
what
could
you
be
have
fine.
observed.
Right.
Okay.
And I think the thing is, we don't actually have a coin to flip. It's already been flipped, and you generated the results D.
So the D is given to you, not the coin.
Yes, right. That's my understanding.
Okay.
And then now we're trying to figure out if we want to know statistics about the parameters, we need, in a frequentist approach, we need to have a bunch of data sets to work with. And then we'll generate whatever the estimator is, that delta function, we'll generate those, and we'll look at the distribution of the theta hat. And the two ways to do it is, one, you assume that you know what the distribution is, so you just come up with the parameters and then you sample from that distribution multiple times. And then the other approach we haven't hit yet is that you essentially sample with replacement, sample n data points from the original data set with replacement. And that's the non-parametric bootstrap. That makes sense? Any further questions, or are we ready to go?
Yeah, just before we move on from bootstrapping, just mentioning that this is not like exhaustive. There's a bunch of other ways that you can resample your data set. So if you're in like a Hadoop shop, you can use a Poisson bootstrap, for example, and that'll give you a different approximation of this sampling distribution.
Okay. Okay. Then here they show, this graph was kind of nice, shows two different approaches to, or an approach to bootstrapping versus a Bayes posterior. And I think it's for a small number of data points and a large number of data points. And the two takeaways are, for small number of data points, bootstrapping doesn't, I mean, that's kind of looks similar distribution. This would be a beta distribution, I guess. Is that right? It looks somewhat similar as the Bayes posterior. But once you get up to bigger numbers, then they're looking pretty similar between these two. And I've seen other things where they talk about, this ends up being kind of the poor man's approach. Well, in fact, they talk about it, I think, here, that it's the poor man's approach. It's cheap, it's close. And by the time you get up to the large numbers, they're very similar. Yeah, this is where they use the term, think of the bootstrap distribution as a poor man's posterior. Okay, this next concept, so most common estimator for estimator is the MLE, maximum likelihood estimator. When the sample size becomes large, the sampling distribution of the MLA for certain models, I'm not sure what certain is, becomes Gaussian. This is known as the asymptotic normality of the sampling distribution. So that, a couple of things, is that, does anybody know, is that like the central limit theorem?
Yeah, he's like deliberately not using the phrase, and he's also not mentioning like the law of large numbers for some reason, but that's where this result comes from. Like the MLE being asymptotically normal is a special case of that.
Okay. Does that also mean that the only distribution that you can model this way with frequentist would be a Gaussian distribution?
So if
No.
I could jump in, no, the whole point is that you could, for example, have distributions that are very not normal looking. They could be bimodal and skewed and whatever, but the mean of that gnarly looking distribution, if you sampled it 1,000 times, the distribution of different mean values you get might well be normal.
Okay.
So you're taking advantage of the central limit theorem in that by having the mean of that gnarly thing, you can now assume like the size of the tails and use your frequentist approach to say what's the chance that our data lines up within the confidence intervals, because we think that thing is going to be normal even though the distribution itself is not normal. That's me saying it in kind of non-technical terms.
Okay. Is it the case that when you talk frequentists, their kind of view of the distribution or the uncertainty on the parameters is it always Gaussian then or not?
No, there's
Okay.
there's like two layers of assumptions. So the first assumption is like IID. And so if IID happens, then you can appeal to law of large numbers and central limit theorem for means and summary statistics that are similar to that. And then secondarily, there's distributional assumptions like a Gaussian distribution or a binomial or whatever. And then that can give you some more specific things to work with.
Okay. Okay.
And for the bootstrap, for example, so imagine instead of like, if his example weren't coin flips, but it were like, I don't know, number of tumors in a lab rat or something like that, that's like a weird distribution. It's not binomial. It's not like every rat has an equal chance of getting a tumor or whatever. Like some of them are like really unlucky and some of them are fine.
Mm-hmm. Okay. Okay, so they're just talking about the mean in this case then for the normality. Okay.
One question about the MLE. You know, the likelihood function in the base case, they define it, you know, it's a parameter of the thetas. Is it defined differently in the frequentist case, or I'm wondering how I should think about the likelihood function for computing the MLE?
The equation will be identical typically. It's just the differences is, do you think of the thetas as random variables, just like anything else, or do you think of them as like fixed for the population, and then the variance you're observing coming from sampling from that population?
I see. So the function, you know, at the end of the day, both are functions of theta, and then you just find the argmax to get your thetas. Okay. Thanks.
Okay, then I'm rolling along to 331. So this is one of the things he does quite often that I don't really like, where he references forward. He uses a term and then it's defined later. But so what he's saying here is that the Fisher information, let's say generative, means convergent distribution. So because this becomes a normal, I guess that's the error, the difference between the true and estimated parameters becomes a Gaussian distribution with zero mean. And then the variance is defined by this Fisher matrix of the true parameters, or the inverse of it.
Mm-hmm.
I don't know Fisher matrix enough except to say here where it talks about the Fisher information matrix equals the Hessian of the log likelihood. So it measures the curvature of the log likelihood surface at the true parameter value. Well, at any value, I suppose, but in this case, the true parameter value. Okay. So as it gets bigger, it goes to a Gaussian centered on the true parameter with a precision equal to the Fisher information matrix. And a little more introduction of the Fisher information matrix, which is related to the curvature of the log likelihood. This little thing about the Jeffreys we'll see a little bit later. And I think here he's kind of defining it as the covariance of the score function. So the score function is the gradient of the log of the distribution. And the Fisher matrix is defined as the covariance of that, which this term, at first I thought looked like it was missing a term, because I assume this is kind of the matrix equivalent of the x squared type of thing. But later on, he says lemma 331. So this would be expected value of the score function equals 0. So it's kind of it when it's the score function is the gradient log p. Then the mean, I guess, it's kind of zero centered. Okay.
Yeah, I have a question. So equation 3.38, right, which was right above on page 107.
Yeah.
So this F theta star, that's the Fisher information matrix, right? So is that the precision in some sense? Like, the inverse of variance is the precision. So is this what this represents to some extent? Just thinking out loud, or is it? Anyway, I don't know if anyone has any thoughts on that.
Yeah, you're exactly right.
That's
Okay.
easy.
Thanks. So why, again, why wouldn't they use the term precision here? Just wondering, which is a more commonly known term in statistics.
I think he actually does use the word precision in the paragraph below equation 338. So if you look at the fourth line of that paragraph.
Line 13. Okay.
Yeah.
Oh yeah, there's line
thanks.
numbers. Sorry. It's like tune them out.
Okay. Any more discussion or moving on?
So my only question is, Neil, since you seem to be the person answering a lot of questions, how important is it I understand this Fisher information matrix? Is it okay if it kind of like goes over my head a little bit and I'm just like nodding my head? Yeah.
Yeah, I would just kind of roll with it. It'll pop up in a couple other places. It is related to some information theory stuff, and it'll pop up in at least one measure of divergence. But like now you know which page to flip to and diagnose it. And I think the other thing that's important is there's this relationship between there's like two things that are equal. So there's the expected value of the first derivative, and then there's the second derivative, and those things are equal. So I think that's one thing that he's called out there.
I would like to add that score, the next section on the score function, is that right? That's what it is called? The score function. That is maybe revived, or for lack of better words, in the diffusion models. So it's highly important, and that's what became the, when the original diffusion model came out, the score-based diffusion models actually leveraged this quite a lot. But that is, far out in our reading club right now, but that's when it becomes important again.
Yeah, I've definitely seen that stuff. But that was still the score function. That wasn't the Fisher information matrix. So
So this is kind of what direction is downhill, and this is how curvy the downhill is. Is that right?
Yep.
Nope.
Okay. Cool. Thank you.
Okay. I'm sorry, was that a no or a yes?
That was a yes.
Oh, okay, good. Okay. So the Hessian measure the curvature of the likelihood, which tells us the likelihood function can identify the best set of parameters. If the likelihood function is flat, we cannot infer anything about the parameters, but it's at the delta at a single point, we can uniquely determine the values. So it's this idea of how peaky it is, how well we can localize, I guess, the MLE.
So to tie it back to what we did earlier, could we say that, if you have few samples, it's kind of flat, and if you have a lot of samples, it becomes that peaky delta function?
Right.
Yeah, cool.
Yeah. Okay, I don't know if there's anything else here that is worth making note of. I'm going to just kind of flip through pretty quickly for a while, I think. These seem like just equations. If I want them, I'm going to come back and look at them. Some of the comments are occasionally interesting. This one, but then this is the expected value of, oh, is that the H is the Hessian? Yeah, okay. Is H sometimes represent entropy? I thought.
It does, yeah.
Yeah, okay. That's why I was a little confused, but it looks like from the equation, it's just the Hessian. Okay, so for
he's defined it right above that, I think, as that
okay.
Double differential.
Okay. Here they just drive them real quickly. The Fisher for a binomial is just, I guess, n is the number of samples and the parameter theta. So I guess what this means is your number of samples goes up, the Fisher gets bigger, so the 1 over Fisher gets smaller, so your variance gets smaller and smaller. So that kind of feels right. For a univariate Gaussian, I think the Fisher now is a matrix because there's 2 parameters. There's the mean and the variance. And so you end up with 2-dimensional, 2 by 2, but again, it seems to be only related to the variance.
So that's actually kind of intuitive, right? That if it's expressing how peaky it is, it doesn't matter where the mean is, it just matters what the variance is.
Yeah, yeah. I don't know if it's intuitive for me why there's a term here. I get the v squared term, I think, but I'm not quite sure about the v term. But
so there's a curvature on the mean and then the curvature on the variance.
Right.
So you need different numbers for those two things.
Yep. Yeah. Okay.
And then you have zeros. It's a diagonal matrix, so there's
No
they're
interaction between
independent.
them. Yep. Okay. Thanks. That clarifies. I trust this for logistic regression. It's all a big matrix one. Anybody want to say anything on that one? Kind of the same on the exponential. Here, I guess the Fisher, I think they drive it in the next one. I guess they have a Fisher matrix for each term. What is it? This is the moments, are they? Is this one thing I wasn't clear about? This tau in here, is that the Cauchy distribution? Or is that the tau they defined? I remember seeing this earlier. When I looked it up, it said Cauchy distribution.
Yeah, but in this case, I think that tau is, is for the exponential family back in section 2.4.
It's the parameterization, Yeah. Okay.
Yeah, that was what I thought too.
Okay, all right. So I won't go into that too much more unless anybody else wants to cover any of those parameters.
Okay, there's a lot of different Fs. Is that significant? There's an FM, F8 or something.
So I think it's just the Fisher matrix for that term, right? That here they're doing.
There's also an
exponential.
F alpha.
These are all, isn't N and M were all terms of the exponential family parameterization.
Okay.
So each one, I think, is ending up getting a Fisher matrix, if that makes sense. Hold on one sec, guys. I'll be right back. Okay, so rolling on. So confidence intervals. So this one seemed like it was a pretty big issue and difference between Bayesian and frequentist approach. So they start, I think, by saying, be sure it's different than the, what was it, confidence interval, and the other one was credibility region that they use in Bayesian. So confidence intervals then, they are, if I understand correctly, they're saying that given an interval that can be derived from the data, what they mean by confidence interval is that the probability that the theta is in that interval is equal to 1 minus alpha. So what the number captures for you is that for all these different data sets, they're going to compute an interval, and it's the probability that the theta exists within that interval.
I believe that's the common incorrect way of defining the confidence.
Oh, okay. Can you define it correctly then?
So I'm gonna possibly butcher this too, but basically the credible interval, or whatever it's called, means that because you treated your theta as an unknown and you treated your data, right, as what you know, then there's a 95% chance that theta falls within the interval that you picked. Okay. The frequentist thing, which the author is calling counterintuitive, is that you're treating the parameter as some hidden true unknown, and you're saying 95% of the time my data will cover the parameter, the true parameter. But that's not the same thing as saying there's a 95% chance that the parameter is in this range. And that's what's confusing. Neil, did I get that right?
Yeah, and just to kind of add on to this a little bit. So this confidence interval that you're constructing, the lower bound and the upper bound are both themselves random variables coming from the data set, right? And so that's like an important thing to think about. It's not about the distribution of the parameter, because that like exists in Platonic space. But the variability that you're seeing is coming from your sampling procedure or whatever, and manifesting itself in these upper and lower bounds.
Also, he mentions hypothetical data set, D tilde. I don't know if this seems like it relates to what you said earlier, Ted.
Yeah, I mean, I actually feel like I understand it a little better now that he's actually defined the credible interval or whatever, because I can contrast the two. Up till now, whenever anybody has said define the confidence interval, I'm like, I know that it's not 95% of the time it falls in the confidence interval, because I know that's the fallacy. I just don't know what the right one is. So now I feel like I kind of can give the correct definition. I do find it very unintuitive, and probably, as much as I struggle with it, could never define it to my boss, to a layperson, correctly.
So it seems like, if I understand this right, what I'm reading is that when you express a confidence interval, which is the frequentist approach, essentially you're saying you're doing multiple samples of the data set. Is that right? And then you're determining this region from that?
Yeah, so essentially, if you were to take several samples and calculate a confidence interval many, many times, then 95% of the time, your intervals would hold the true fixed parameter theta, because theta is an unknown but fixed number. It's not a variable like it is in the Bayesian credible interval.
Okay. That was nicely said.
Yeah.
And
I think
that
it says that
intuition
in
is what
43
powers the
and-
bootstrap.
Sorry, go ahead.
Neil, can you say that again? You guys stepped on each other.
Yeah, so this idea of, hypothetical samples, that idea is what powers the bootstrap and allows it to recover the sampling distribution.
And Janet, did you have something to say?
Yeah, I was just saying that, lines 43 and 44 say what somebody said earlier, right? That
Yeah.
95% of such intervals will contain the true parameter data.
Yeah. And then he expresses it as, however, it doesn't mean that any particular data set that the theta is within the interval from that data set with 95% probability, which is the other. I'm going to read, there was a paper that I found talking about Bayesian versus frequentist, that there was one line here that I thought kind of helped. It said that the Bayesian credibility region answers a question about the value of theta itself, the probability that the parameters is in the fixed credibility region, while the frequentist confidence interval answers a question about the procedure used to construct the confidence interval, the probability that any potential confidence interval will contain the fixed parameter. So I think that's saying what we talked about here. The part that was interesting here is then in this paper, they're basically saying they're just expressing two different things. And they ran Monte Carlo simulations and demonstrated that both are true. They just are expressing different things. And the problem is that most of the time, when we look at this region that we care about, what we really won't think about is the credibility region that, that what's about the parameter theta itself, not the frequentist approach or interpretation.
Yeah, so like my very loose analogy would be, you're taking a chemistry class, and if I said, oh, there's a 95% you did that lab experiment and you produced some chemical reaction and you said, oh, the whatever it is you're trying to figure out, the formula for this chemical or the molecular mass of this chemical, I came up with is, 50 or whatever, right? And if somebody just says, there's a 95% chance that you did that experiment correctly, right? Mm-hmm. If you're in that 5%, it says absolutely nothing about the relationship between the true answer and the 50 that you got.
Mm-hmm. Yep, that's also a nice analogy. Yep.
So as a counterpoint, if we're comparing it with the credible interval, in order for the Bayesian machinery to work, you have to plug in a prior, right? And so if that's a bad prior, you're still SOL, right? Like, and you won't know because you have a finite amount of data.
Okay, that's fair. But at least I will define the credible region correctly and say there's a 95% chance under my assumptions, which includes my prior, that the whatever, the molecular mass in my case is between, 45 and 55.
Yep. Okay, right. Still a confusing point, but but I think we probably need to move on. But it seems like it is a pretty important one.
I liked what he said in lines 3 to 5 on that page.
Okay, yes, I agree. That one really resonated to me. So I'll read it. So we, so we see that the concept of frequentist CI and Bayesian CR are quite different. In the frequentist approach, theta is treated as an unknown fixed constant. The data is treated as random. In Bayesian approach, we treat the data as fixed and the parameter as random. Yeah, that's really a nice succinct difference between them two.
Yeah, so I was wondering, like if you think about the coin toss, like the the what's the parameter of that coin, the bias of that coin, in essence, you can think of it as fixed, but in the Bayesian approach, it's modeled as a random variable because we don't know it. And in the frequentist approach, it is that fixed thing, but then the data that's coming out of it in each sample that you take, is the random output, something like that.
Yeah, I mean, I find the Bayesian approach to be compelling because what truly is unknown is how fair is this coin, right? It's kind of weird to like assume it's fixed and then do all this other stuff. But to Neil's point, if you said that we were gonna, divide today's dessert by flipping coins to see how much each person got, and I was absolutely sure that you had an unfair coin. Like my prior is that the odds are 1,000,000,000 to 1 that it's a fair coin against it being a fair coin, right? That super strong prior belief means that even if you flip the coin, 100 times and it comes out 50-50, I'm still going to believe that it's unfair.
Well, you would believe it's more fair than where you started, but still incredibly unfair.
Yeah, I would move from like 1,000,000,000 to 1 to 1,000,000,000 to 1 or something like that. You know what I mean? So that's the problem with the priors, is that if your prior is really, really wrong, then
it's like your starting point, right? You update your belief as you go.
Right. So you're updating your belief, but if your belief, right, was incredibly, incredibly wrong.
So it's almost like in any result, the posterior has to be described by both the data and the prior. You always have to take into account what was the prior that got you to that posterior.
Yeah, I was looking at this much lighter treatment on Bayesian statistics, and the way they said it basically was like you have a belief going in, and the posterior is your updated belief after seeing some data. So.
But it seemed like one of the big complaints in the scientific community is this idea that you have to come up with a prior before you analyze the data, and that prior affects your result. That seems to be a big complaint. And if you looked at the history of it, that was one of the things that was driving people away from it.
Yeah, I think it's a fair criticism, or it's a fair concern. And if you are, I don't know, because the world isn't very Bayesian, I don't know to what extent people would abuse Bayesian statistics in order to claim that they had interesting findings. I do know that scientists absolutely abuse the frequentist statistics to say that their experiment proved that blah de blah causes cancer, blah de blah cures cancer, blah de blah, blah de blah, blah de blah.
Yeah, I would love to. I think we'll go to the next section here, but when we get there, if somebody has an example of how that is used to make a false claim.
Let's talk about the p-values.
That'd be a good color for me. Okay, let me keep moving this along because it's already 5 after 7. So p-values, this isn't something I've worked with, but p-values, I guess, are used in the null hypothesis testing. If I understand it, it's kind of like what I've read. If there's something that is the common belief, and that's called the null hypothesis, and then there's this alternate truth or alternate explanation that you want to prove. And the way the null hypothesis works is you disprove the null hypothesis, or you say that it's highly unlikely, and therefore that makes the alternate more probable, I guess.
Right. So this is all set up in terms of double negatives that always confuses students. Like when I was teaching intro to stats, this was absolutely one of the things you just make them memorize and drill and kill, instead of like, memorize the thing and do it correctly and then understand it later kind of thing.
Neil, can you tell me why is it that, what's the advantage of a null hypothesis rather than proving the alternate?
So there's lots of null hypotheses that would affect decision making. So for example, if your null hypothesis is that like Tylenol is at least as effective as Advil or something like that, that's kind of a natural null hypothesis. And then if you collected data, you would test against that assumption, right? A null hypothesis is kind of like a baseline assumption. Part of the gamesmanship of p-values comes to having stupid null hypotheses, right? Like, like equivalence is not always a correct null.
Right. Yeah, that's kind of what, to me, it looked when they were slamming the null hypothesis testing. It seemed like the problem is that the null hypothesis and the alternate are not described as a way that that spans all possibilities. And so you can use it by disproving the null hypothesis. You can use it to prove something. You claim to prove something, but actually there was yet another explanation for it.
Right, and depending how pedantic your professor will be, you will only ever reject a null hypothesis or fail to reject it. You would never accept an alternative hypothesis. That's part of the pedantry of this procedure.
Oh, okay, so that's what you're going to do.
Yeah, and I don't think you ever sort of disprove or the HZ, the null hypothesis or anything. You just say that it is super unlikely.
Yeah.
And so pedantically, you also set your goal below which you would say that it is unlikely before you do your experiment, so you don't change it to make it unlikely after you did.
So you don't cheat, but people do cheat. So Roger, I think like a common example that I've heard is if you have a website with so many users, so let's say Amazon or something like that, right? And so you set up a test to see whether this new web page is more popular or people buy stuff, you know, more than the other one. So to Neil's point of if you have a overly specific null hypothesis, which says that the two web pages are equal, okay? If you have such a popular page that you have 5 million people going to both the control and the treatment, you're going to be statistically significant. You're going to be in that p-value range. So you're rejecting the null hypothesis that the two pages are equal, but that doesn't mean that there is a specific alternate hypothesis that the new page is 5% better or whatever. So basically any amount of difference, the new page is 5% better, 0.5%, 0.05, 0.005% better. Any difference will be statistically significant in the frequentist world just because your N is so large.
Okay.
But that's because you chose a null hypothesis that the two are equal. So Neil, correct me if I'm wrong. If you chose the null hypothesis such that the new web page is no more than 2% better, then you're going to have a much harder time disproving that null hypothesis, because now you need to actually beat 2%. You can't just be 0.0005% better and reject the null hypothesis.
Right, and like once you've gone through the mechanics of distilling a data set down to a p-value, like the effect size is gone, right? And the effect size is, for a lot of practical applications, the more important thing than a p-value, which is this, you know, summary statistic of your compatibility of your data set with a null model.
But in particular, it's what you said. It's the choice of the null hypothesis, like the null hypothesis being that they're equal. I could have made the null hypothesis a much harder hill to climb.
And well, and to also relate this back to the Bayesian stuff, part of that model includes distributional assumptions. And, you know, this goes into the likelihood, like if you're a Bayesian, you can fall into this trap too of choosing a bad distribution, and then, you know, it's kind of garbage in, garbage out at that point. But typically Bayesians are not making like make or break decisions based off of a single p-value.
Yeah, but I mean, in theory, if pharmaceutical scientists were getting billions of dollars based on their Bayesian statistics proof of their drug, maybe they would be driven to abuse Bayesian statistics just as badly as they abuse frequentists today.
I think that's starting to happen in bioinformatics, where you get people's DNA or whatever, and they're looking for different genes on chromosomes or whatever that relate to different health outcomes. Like it, that game's already in play.
So Roger, I hope this was helpful and not a sidetrack on the section.
No, I think it's still a little confusing for me, but it is helpful. I did want to check one thing. I thought I heard Neil say that kind of proper use of null hypothesis testing would allow you to disprove or reject the null hypothesis, but it doesn't necessarily confirm the alternate hypothesis. Is that right?
I mean, it doesn't even conclusively rule out the null hypothesis. It just says if you're making a decision based on this, you're only going to have false positives 5% of the time.
Right. Okay.
And I think, if you look at line 5, like it's something, the statement is something like H0 is unlikely, therefore H1 is likely. There is no black and white. It's how unlikely and likely things are.
Right, and the where you have like a specific H0, that's common between both of these frameworks, but the H1 is a little different. As a frequentist, you would have HA is the set complement of H0, right? Versus as a Bayesian, you can specifically have an alternative hypothesis and then go through the Bayes machinery and get a posterior probability of H1.
True, that's right. Yeah, and you could also compute like the ratio, for example.
Right.
Oh, yeah. Okay, that helps actually.
Yeah. This example was helpful for me and kind of walking through this equation down here, where they basically, what did they say? Someplace that the null hypothesis ignores P of D given H1, the alternate hypothesis, as well as the prior. So it's kind of like doing it with and that was the problem with this American and congressman example. I think where they said it's the probability of being a congressman and not an American is 0.
And so this is like the core like fallacy that people make. So p-value is not this, probability of the null hypothesis, right? It's, if you were to do this like hard decision process, you would have 5% false positives or less.
Mm-hmm.
That's like a different promise and like you can get into the decision theory of why that could be like good or bad. A lot of times like 5% is like the wrong magic number to use.
Mm-hmm. Okay. Anything else anybody wants to say about that? I think that this pretty much captures it. So it's kind of, it's saying the wrong thing, what we
it's quite clear the author doesn't really like that approach.
Yeah.
Oh, and I will call out this citation of Jim Berger's book. That decision theory book is absolutely fantastic. So he's actually written like 2 editions of it. The first one is kind of like a straight up decision theory, and then he goes Bayesian for the second edition. So I've read both. It's a great book.
Cool. Okay.
Thanks, Neil.
Yeah.
That's cool. And are you suggesting reading both, or?
I mean, if you're in grad school and you have time to kill, definitely. Like.
Yeah. Cool. Thanks.
Okay. So we're down to 15 minutes left. So let me, unless there's anything else, Neil, you wanted to throw in, or anybody else?
Also he's citing Don Rubin. His Wikipedia page is also quite stacked. So that's the guy that, or one of the people that came up with like the EM algorithm for missing data. Very influential on the census and causal inference also, and is also a statistician that is sometimes a Bayesian and sometimes not. So that's also a name to be, whenever you see that, to like take note.
Okay. Okay, conjugate priors. Let's see, I'm not sure. We've already kind of talked through some of this definition, just that the posterior and prior have the same form given, and it's called a conjugate prior to the likelihood function. There's a wiki page that has a bunch of these. I don't think, unless anybody feels otherwise, that there's a lot of value going through all of these in any detail. They exist.
I mean, the thing is that if you have like one exponential family and the conjugate prior is known, then you can use the now the words are blanking me, but the formula for the distribution. You can have a precise mathematical formula for it.
The closed form.
Closed form, thank you. Yes.
Yeah. Yeah. It also, I noticed as you go through here, when they're expressed in the precision form, they all have kind of this easy update that, you know, how the precision increases. Yeah. Let's see, I'd made note to myself here. This one, posterior of y given the sigma squared. Is this, would I think of this like is sigma the observation variance?
Right, and then in this example, it's like fixed. It's a known constant.
Okay. Like a measurement error. I've got this noise on this scope or something.
Right.
And I don't remember why these questions came up right here for me, but
so one question about that, is it used anywhere in practice, like, you know, where the sigma squared is a known constant, or is this only for sort of a theoretical exposition that they do this thing?
So if you were in a situation where you had like some pre-existing literature where someone else had like, I don't know, come up with this to like a high degree of precision, like as a Bayesian, you're allowed to like piggyback off of that.
Okay.
And I would imagine that many of these theories have been built around the physical models of atoms or whatever needed to be described 100 years ago. And they may have some assumptions about variance that does not change, but they are maybe trying to figure out the position of, I'm just making it up honestly, but I'm thinking out loud that, you know, could be a derivative of how it was common in the physical world, and variance doesn't change, but then your mean position changes.
Yeah.
Okay.
I'm going to ask it again because I might have misunderstood the response then. In this case, sigma squared is the observation variance. So that's like my voltmeter has noise on it. And the noise is captured as the sigma squared.
So if you see 10 and 11 lines, Roger, like it says sigma squared is a known constant. So it's like somebody gave it to you.
But it gave it, so it's not part of the prior. It's my observation noise, right?
So Roger,
observation noise. I don't think it's like
it could be. I think measurement error could be a good example for where we think we have a known sigma squared. Okay, but it's not the variance of your samples of your measurements. It's just a predefined constant known. Here's my meter. Here's the variance on any measurements. You've been told by fiat, by God, that that's the distribution you'll get whenever you measure something.
Yeah. Okay.
Yeah, and I think I have the same trouble as you, Roger, because I was like, where would you use such a thing? You know, or how would you be given this sigma squared? So yeah.
So one procedure that's very common is to standardize your data, right? Which is subtract off the mean and divide by the variance. If you were given a data set where that has already been done and all you can see are the z-scores, then you know that the variance is 1.
Mm-hmm.
I also wanted to know, so I'm, I don't know how to pronounce this word, so I'm just posting it on chat. So this constant variance apply, for the assumptions of almost city or a city. I don't know how to pronounce that word, but if you got the chat message,
Yep.
then one of you can. So
Yep,
that's a very common assumption, right?
Yeah, yeah, that's exactly it, is constant variance.
Right, but what I'm trying to say is that that's a very, very common assumption in a lot of regression models as well. Oftentimes, right?
Yeah. And Gaussian processes, if you caught Ravine's Gaussian process webinar.
Okay, so again, I'm not sure why these two questions came up here for me in this section, but I was wondering if you have a prior that's too strong or too weak, what's the consequences of that?
So in this simple model, there's a couple things that can happen since we're only updating the mean. If your prior is too strong, your posterior is just going to look like the prior. And if it's too weak, then it's just going to look like the data. And if you're looking at like credible intervals, if the prior is too strong, the credible interval is going to be very tight around that prior. And if the prior is too weak, it'll, again, just be whatever the part coming out of the likelihood is.
Is there any sort of intuition or rule of thumb of how to know if your prior is too strong or too weak?
So whenever my clients get revise and resubmits and the reviewer is like, oh, try it with the different prior, then like you go and redo the whole thing with their prior that they like and you get the same answer. So
okay,
like, I don't know. If you have a good data set, the prior doesn't matter that much.
Okay.
I think at the end of the chapter, he does talk about testing. And one of the things is if you try different priors and you get very similar answers, then that is somewhat reassuring. And if you try different priors and you get very different answers, then that means that your prior choice is very sensitive to that choice. So I think it's good to be informed by how sensitive your analysis is to that choice.
So kind of sampling the priors.
Yeah, and as we get into the multi-level models and that kind of stuff,
exactly.
explicitly do that.
And then I think about it just in practical terms, like if you do some machine learning thing, you've got some hyperparameters, right? And if you tweak the hyperparameters and you get the exact same answer, then like that's very comforting to know that your choice of hyperparameter was not super critical.
Yeah.
But then there's double descent. You never know.
I'm not saying no. I'm just saying it's comforting.
Right.
Okay, this was the quick picture then that with a weak prior and a weak prior over here and a strong prior over here. So it kind of captures it, what you said, Neil, about, in this case, the posterior is very similar to the likelihood.
And this book, and in particular this figure, helps with that other description I said, where you have your belief going in, and then you have your evidence, and your posterior is basically always going to fall in between. Because you're going to update your belief based on the evidence. And if your original belief was weak, you're going to move really close to the evidence. And if your prior was super duper strong, like I said, 1,000,000,000 to 1, this is fair coin, it's going to move like 1 iota. That's it.
Yeah. Okay. Nope. I'm going to try. So we got like 5 minutes here. I'm going to zoom along. People just yell if you want me to stop. So for Gaussian, the posterior mean and mode are the same. Yep. Okay. I didn't get a lot out of this. These are just more, there's a, what happens if you don't know both of them? Oh, yeah, okay. So what if you don't know both of them, I guess, was one. I hadn't, this was a new distribution that I hadn't seen that covers the norm and the variance. Multivariate, here we go. It's just the multidimensional version of the same things we've been looking at. Anybody see anything? Once again, that kind of observation that here, that these confidence factors, when you express these in, or format these in precision, it's just a nice, simple, you get more examples, you get more data points. They increase the confidence or the strength of it. There's someplace else also where they talked about essentially getting a bunch of samples with a particular precision is basically the same as getting one sample with the higher n times the precision. That was an interesting one. This is the numbers for the exponential family.
Hey, Roger, I'm going to
Yeah.
have you pause for just a second. I'll give you your last minute or two. But
Okay.
for people who weren't here at the very beginning, next week for this meetup, we are going to post the basic Zoom link in the meetup event, but you're going to need the password. And so you're going to need to join Slack and look in the book club for what the password is for the meeting next Tuesday. So I announced it at the beginning. I just want to make sure in case any people joined late. I'll put that all in the meetup description, but just kind of wanted to warn you to expect. So many of the other ones, you just click the link and you're in. But just as a way of further avoiding possible hassles with Zoom bombers, we're just going to take that extra step and see if that's too annoying or if you guys think it's a reasonable thing to do on a regular basis.
Okay, so the beyond conjugates, one was, it was kind of interesting that they said a mixture of conjugates. This is where they have distributions with a, what do they call it, a indicator function that indicates how much of each of the two distributions is being added together. At the same time, I think they said somehow, fortunately, the resulting mixture prior is still conjugate. So this is still conjugate. It's not a non-conjugate prior. This one was kind of interesting, caught my eye that these heavy-tailed priors are actually what we like because they take into account, put more emphasis on the data. Yeah, in general, priors with heavy tails tend to give results which are more sensitive to the data, which is what we usually desire. However, heavy-tailed priors are usually not conjugate. I don't know if anybody wants to say anything about that. It seemed like there's a conflict.
Yeah, so if you don't have the closed form, they're more of a pain in the neck to work with. My question is, again, I'm probably looking to you to answer, but when we say robust, do we really mean more robust or do we mean robust? Because like, I've read it like, oh, and now it's robust, you know, like robust outliers. And like, or do you just mean it's like slightly more robust?
Yeah, so especially in kind of the econ literature from the 80s, every time you see the word robust, you have to ask like, robust to what? And so for a lot of that stuff, you might have robust standard errors. And so those will have better coverage properties, but they say nothing about the bias that could be going into the model. So you could still have the wrong sign on your point estimate, right? So whenever you see that word, say robust to what?
Yeah, but like even if like you have like a robust linear regression or whatever, like it's just more robust. It's not really like I don't know how to say it, but robust and I can wipe my hands and be completely sure.
Are you looking for like an absolute measure or something, Ted? Like
no, I'm saying that when I first was introduced to robust regression, I didn't know what it was, and it sounded to me like they were saying it was absolute. Like, oh, here's this amazing thing. It's robust. And now I'm thinking, well, it's just got a heavier tail. It's like more robust, but it still could be not robust enough.
Mm-hmm.
Is that a dumb question? I don't know.
No, I think it's an important question because that word is used and it conveys like some kind of like guarantees of reliability that may or may not be there.
Yeah. All right. That's really what I was trying to get at. Yeah. Okay. Thanks.
I have another dumb question in terms of a heavy tail. Does that mean it's tending towards uniform to some extent? The distribution of prior?
Literally, the word heavy just means more tail than a normal Gaussian distribution. It doesn't have to be crazy more. Does that help, Dave?
Okay. Yeah. Yes. Thank you.
Okay, I'm going to wrap up in 1 minute here. So non-informed 3.5 non-informative priors, they talk about different ones. This maximum entropy. So I think what they're saying is you can optimize these for maximum entropy, and then do that. So maxent prior meets certain constraints, the maximum entropy that can satisfy those constraints. And they had some examples here of where they per certain constraints, like it wants to have a mean of 1.5, but it's a distribution PDF, so it's got the integral has to be 1, and they just optimized it. I'm assuming there's some sort of numerical optimization or something like that on that. The Jeffreys prior.
Would it be fair to say that these uninformative priors, it's sort of the least amount of me putting my thumb on the scale with a strong prior? So if I get a strong answer with an uninformative prior, then that's a pretty convincing answer. Would that be a way to intuit?
That's how I am interpreting it, Ted. Because the more uninformative it is, the more my data would tell me.
Right. And so then if you get a really, narrow, precise answer, then that's saying that you didn't get that just because you started with a strong prior and you tipped the scale.
Yeah, I mean, beyond what you're saying, I don't have any intuition. Neil or someone else may chime in if they have more.
Okay, we got 2 left. Jeffreys priors. This one, I think that the key characteristic is that it's invariant to how we parameterize the model. And here we see that the Fisher matrix come up again, that Jeffreys prior is proportional to the square root of the Fisher matrix. And they prove it there. And then they go through a bunch of priors for our distribution, which I'm going to skip right now. Invariant priors where they have, I didn't really follow why you would have a translation invariant prior and a scale invariant prior, but they say one's proportional to 1, which I guess just means it's a constant, and the other is, or is that essentially like a uniform, I guess would be, and then scale invariant is proportional to 1 over the variance. And this one I thought was kind of interesting. A non-informative prior that you derive by maximizing the expected KL divergence between the posterior and the prior. So I think what they're saying is for a bunch of posteriors, if you have a bunch of posteriors, you try to maximize the KL divergence, the difference between that distribution or that set of posteriors and a given prior. Neil, you heard of that one before?
I don't know. In grad school 10 years ago.
Okay. Well, all right. I thought it was interesting because it's kind of saying, yeah, make the prior as non-informative as far away from any of the distributions you're going to arrive at. And that completes 3.5. 6 minutes late.
Nice. Thank you, Roger.
Thank you.
All right. So the plan is
Thanks,
next
Roger.
week, Jayant's going to take us 3.6 through the end of the chapter. And in 2 weeks, Dave is going to start chapter 4. I don't know. I haven't really read ahead. I don't know if we're going to need multiple weeks. It's shorter than this chapter, but again, I don't know if some of it we can go through faster or slower.
Yeah, I don't know either, right?
Yeah, we'll see. All right. Appreciate it, guys. Thanks for joining us. And we're already over time, so I'm not going to do anything here. But just a reminder, the hope is that people will take turns and help out. I get it. Some of this material is pretty heady. But again, you don't need to be the expert. We're all trying to work our way through this, in some cases, muddling more than others. And so I am gonna next week ask for, I have discussion leaders for the next 2 weeks, but it's really open after that. And I'm gonna ask some people to just step up and help out. Again, just like Roger did, just to kind of walk us through. You don't have to be the expert on it. All right. Have a good week, everybody.
Hey, Ted. Can I
Yeah,
ask a
Roger.
quick question? You had mentioned something about, I think it was a soft introduction to probability or Bayesian versus frequentist, was it?
Oh, I was reading this book that I got. What is it? Bayesian Statistics the Fun Way. It'd been just gathering dust on my bookshelf.
Oh, okay.
So I like powered through it this past week.
If that's something available electronic form, if you could post that on the Slack, the link to it.
Yeah, I have a paper copy. I don't think it's available online, but there
Okay.
are, what is it, like Think Bayes, I think, is available.
Okay. Hmm. And that fits that soft category.
Yeah, I mean, compared to this book, it's like,
Okay.
so I just put it in the chat.
All right. Thanks,
And
guys.
Roger, I'm not sure if the same authors, not the advanced book, but the other book, it also has the same flow, if you may, the foundational mathematics
Oh.
followed by introduction to topics. So maybe looking at that also may help. I haven't looked at it, but I felt that maybe 1 or 2 topics that I looked at, I felt just that, advanced topics is just blowing up the introduction to topics in the other book.
Yeah, that's a good suggestion. So you can look at book 1 also to see if he has a slightly more accessible discussion. There's some overlap between the 2 books.
That's good.
Right.
See you guys next week.
All right. Thank you.
All right.
Yep.
Thanks. Good night.
Thanks. Bye.
Right.